the universe did not always look the way we see it now. Today, we live in a cosmos filled with galaxies, stars, planets, and complex structures stretching across billions of light years. But there was a time when none of this existed. To understand where everything came from, we have to roll back the cosmic clock, step by step, to a moment when space itself was born, and even the concept of before stops making sense. For most of human history, people believed the universe was eternal and unchanging, or that it had been created once in a finished form and then simply persisted. Only in the last century did we find solid evidence that the universe is expanding, evolving, and has a finite age. When astronomers measured the light from distant galaxies, they saw that this light was stretched toward the red end of the spectrum. The farther away a galaxy was, the more its light was redshifted and the faster it was receding. This discovery, associated with Edwin Hubble, meant that space itself is expanding. If everything is moving away from everything else now, then in the distant past, everything must have been much closer together. Imagine running the movie of the universe backwards. Galaxies drift toward each other, clusters contract, temperatures rise. If we rewind far enough, we eventually reach a state in which all the matter and energy in the observable universe were compressed into an unimaginably hot, dense condition. This is the starting point of what we call the Big Bang. It was not an explosion of matter into empty space. It was the rapid expansion of space itself from a highly compressed, high-energy state. Space, time, and the basic fabric of reality began their recognizable evolution in that moment. To grasp how extreme that beginning was, we need to zoom in on the first fractions of a second. The earliest phase we can meaningfully talk about is called the Planck epoch. It lasted only about 10 to the minus 43 seconds. At that scale, our current theories break down. Quantum mechanics and general relativity collide, and we do not yet possess a complete theory of quantum gravity. We do not know exactly what happened in that earliest instant, but we know that the universe was incredibly hot and dense, and that the usual notions of space and time may not even apply in the way we understand them now. Immediately after this, the universe entered a phase that many cosmologists call cosmic inflation. In an unimaginably brief period, from roughly 10 to the minus 36 to 10 to the minus 32 seconds after the beginning, space expanded exponentially. Regions that were smaller than an atomic nucleus ballooned to cosmic scales. This inflationary burst smoothed out the universe, ironing over irregularities and making the cosmos astonishingly uniform on large scales. Tiny quantum fluctuations in the energy field driving inflation were stretched to astronomical sizes. Those fluctuations later became the seeds of all structure, the places where galaxies and clusters would eventually form. After inflation ended, the expansion slowed from exponential to a more gentle rate, but the universe was still incredibly hot. This was the era of fundamental particles and fundamental forces in their earliest forms. At about 10 to the minus 12 seconds, the temperature was so high that familiar particles like protons and neutrons could not yet exist as stable objects. Instead, the universe was filled with a plasma of quarks and gluons, the building blocks of hadrons, interacting in a dense, turbulent soup. Matter and antimatter were constantly being created and destroyed in pairs. During these early moments, something crucial happened. Matter came out slightly ahead of antimatter. For every billion antiparticles, there were 1,000,000,001 particles. Almost everything annihilated into pure radiation, but that tiny asymmetry left a residue of matter. Without this imbalance, there would be no atoms, no stars, and no people. We still do not fully understand why matter won by that tiny margin, but we see the consequences everywhere we look. About 1 second after the beginning, The universe had cooled enough for quarks to combine into protons and neutrons. This period is called the hadron epoch. Neutrinos, ghostly particles that interact only weakly with matter, decoupled from the rest of the plasma around this time and began to stream freely through space. They still fill the universe today, forming a kind of cosmic neutrino background, although it is far harder to detect than light. Roughly 3 minutes after the Big Bang, temperatures dropped to a point where protons and neutrons could fuse into light nuclei without immediately being torn apart again. In this brief window, nuclear reactions created the first atomic nuclei, mostly hydrogen, some helium, and a trace of lithium. This process is known as Big Bang nucleosynthesis. It left a specific pattern of elements that we can still measure in the oldest stars and in diffuse gas. The observed abundances match the predictions of this theory remarkably well, providing strong evidence that our basic picture of the early universe is correct. After nucleosynthesis, the universe continued to expand and cool, but for hundreds of thousands of years, it remained a glowing fog of charged particles and photons. Light could not travel far without scattering off electrons. Space was filled with a brilliant, dense radiation bath, like the interior of a star stretched across everything. There were no atoms, no transparent space, no stars, just a hot plasma slowly thinning out as the universe expanded. About 380,000 years after the Big Bang, the temperature finally dropped to around 3,000 degrees Kelvin. At this point, electrons could bind to nuclei without being immediately ripped away. Neutral atoms formed, mostly hydrogen and helium. As electrons joined with nuclei, the free charged particles disappeared from the cosmic fog, and light was suddenly able to travel long distances without constant scattering. The universe became transparent. The photons released at that time are still moving through space today. As the universe has expanded, their wavelengths have been stretched from visible and infrared light into the microwave range. We observe this ancient glow as the cosmic microwave background, a nearly uniform bath of radiation coming from every direction in the sky. Its temperature is just a few degrees above absolute zero. Tiny variations in its temperature at the level of 1 part in 100,000 encode the imprint of those initial quantum fluctuations stretched by inflation. In those faint ripples, we see the blueprint for the cosmic structures that would one day emerge. After recombination, there were still no stars lighting up the darkness. The universe entered what cosmologists sometimes call the cosmic dark ages. Neutral hydrogen filled space. Gravity slowly amplified the tiny density variations left over from inflation. Regions slightly denser than average pulled in more matter, becoming denser still. Regions slightly underdense lost matter to their surroundings. Slowly, over tens of millions of years, threads and knots of structure began to form. In some of these knots, clouds of gas collapsed under their own gravity. As they shrank, the gas heated up. Eventually, deep in the centers of these collapsing clouds, temperatures and densities rose high enough for nuclear fusion to begin. The first stars ignited. This happened perhaps 100 to 200 million years after the Big Bang. These first stars were probably very massive, hundreds of times the mass of the sun, burning bright and hot. They lived short, violent lives, flooding the universe with ultraviolet radiation and beginning the process of reionizing the hydrogen gas that filled space. When these massive stars exploded as supernovae, they seeded their surroundings with heavier elements: carbon, oxygen, nitrogen, iron. The universe, once made almost entirely of hydrogen and helium, began to accumulate the chemical building blocks needed for planets, oceans, and living cells. The radiation from the first stars and quasars also transformed the intergalactic medium. Over hundreds of millions of years, ultraviolet photons stripped electrons from neutral hydrogen in much of space. The Dark Ages ended, and the universe became transparent not only to microwave photons, but to many wavelengths of light. As more stars formed, gravity pulled them together into the first galaxies. Some were small and irregular. Others grew into larger disks and ellipses through mergers and accretion. At the centers of many young galaxies, black holes formed and grew by swallowing gas and stars. As matter fell into these central black holes, it heated to extreme temperatures and emitted enormous amounts of radiation, creating quasars, some of the brightest beacons in the universe. When we observe very distant quasars and galaxies, we are seeing back in time to an era when the universe was only a fraction of its current age. On even larger scales, galaxies did not distribute themselves uniformly. Instead, they assembled into groups, clusters, and vast filaments. Our own Milky Way is part of a small group of galaxies that includes Andromeda and several dwarf companions. This group, in turn, lies on the outskirts of a larger structure known as the Virgo cluster. And the Virgo cluster is not alone. It is embedded in an even larger complex called the Laniakea supercluster, a sprawling arrangement of tens of thousands of galaxies linked by gravity and motion. When astronomers chart the positions of hundreds of thousands of galaxies, a striking pattern emerges. Rather than being scattered at random, galaxies outline a three-dimensional cosmic web. Long filaments of galaxies intersect at massive nodes where clusters reside. Between these threads and nodes lie enormous voids, regions where very few galaxies exist. On scales of hundreds of millions of light years, the universe looks like a frothy network where matter traces out something like the skeleton of the cosmos. This structure did not appear by magic. It developed from those tiny fluctuations in density imprinted in the early plasma. But normal matter alone is not enough to explain the speed and scale of structure formation. Calculations show that if the universe contained only visible matter, galaxies and clusters would not have had time to form by today. Something else must have provided the gravitational scaffolding. That something is what we call dark matter. Dark matter does not emit, absorb, or reflect light. We do not see it directly. We infer its presence from its gravitational influence. Galaxies rotate faster than they should if only visible matter were present. Clusters of galaxies contain more mass than we can account for in stars and gas. Gravitational lensing, the bending of light by mass, reveals much more matter than telescopes can see. The simplest explanation is that most of the matter in the universe is in some dark, non-luminous form. It clumps, it gravitates, and it forms a scaffold on which ordinary gas can fall and condense. In the early universe, dark matter began to collapse into clumps and filaments before normal matter could fully respond. These dark matter halos attracted gas, which cooled and fragmented into stars and galaxies. Without dark matter, the cosmic web would not exist in its current form. We still do not know exactly what dark matter is made of. It might consist of new, undiscovered particles. It might have more exotic properties. But whatever its nature, its gravitational fingerprint is written across the cosmos. As the universe evolved, another mystery emerged. When astronomers measured how fast distant galaxies recede from us and how that speed changes with distance, they noticed something unexpected. On the largest scales, the expansion of the universe is not slowing down under gravity as once assumed. It is speeding up. This cosmic acceleration suggests that there is a form of energy associated with empty space itself, pushing galaxies away from each other. We call this dark energy. dark energy appears to make up about 68% of the total energy content of the universe. Dark matter accounts for around 27%. The normal matter that makes up stars, planets, gas, dust, and our own bodies is only about 5%. In other words, almost everything we experience directly is a small minority component. Most of the cosmos is made of forms of matter and energy we do not fully understand. This has profound implications for the past and future of the universe. In the early universe, matter and radiation dominated the dynamics. Gravity pulled matter together, forming structure. As space expanded, the density of matter decreased. Dark energy, however, seems to remain roughly constant in density as the universe grows. Eventually, dark energy began to dominate. That transition happened a few billion years ago. Since then, the expansion has been accelerating. If this continues indefinitely, distant galaxies will fade from view as they cross our cosmic horizon, and each gravitationally bound region, like our local group, will become an island universe in an ever emptier cosmic ocean. Our current best estimate of the age of the universe is about 13.8 billion years. We know this from multiple, independent lines of evidence. The expansion rate measured by Hubble and his successors, the detailed structure of the cosmic microwave background, and the ages of the oldest known star clusters. All these methods converge on the same rough figure. It means that when we look at the most distant galaxies and quasars, we are seeing light that has traveled for more than 13 billion years to reach us. We are looking back in time almost to the cosmic dawn. The story of the universe, however, is not only about distant epochs and abstract energy components. It is also about the slow accumulation of complexity. After the first stars enriched space with heavier elements, later generations of stars and planets became possible. In galaxies like the Milky Way, clouds of gas containing carbon, oxygen, silicon, and iron could collapse to form planetary systems. Around some stars, planets with solid surfaces, atmospheres, and liquid water could emerge. On at least one of those worlds, chemistry crossed a threshold and became biology. Every atom in your body has made an extraordinary journey. The hydrogen in your water and in the organic molecules of your cells was forged in the Big Bang itself, when the universe was only minutes old. The carbon in your DNA and the oxygen you breathe were forged in the cores of massive stars that died billions of years ago in titanic explosions. The iron in your blood was forged in the heart of a supernova. You are literally assembled from material that has been processed in the furnaces of stars and scattered across space. You are a moving pattern made of ancient stardust, temporarily organized into a thinking structure by the laws of physics. When we trace the universe from its hot, dense beginning to the present, we see a sequence of phases. An almost featureless, fiery plasma gives way to neutral gas. Gas collapses into stars. Stars build heavier elements. Galaxies assemble into a web. At each scale, simple physical laws, applied over immense time, produce larger and more intricate structures, from quantum fluctuations to galaxies, from nuclear reactions to biology, from an almost perfectly smooth microwave glow to a sky filled with constellations and galaxies. Cosmologists also wonder what lies beyond the visible portion of the universe. Because light travels at a finite speed and the universe has a finite age, we can only see out to a certain distance. There may be regions beyond our cosmic horizon that are forever cut off from us. The universe might extend infinitely with more and more galaxies, or it might curve back on itself in ways that are hard to visualize. Some versions of inflation suggest that our observable universe is just one bubble among many in a much larger multiverse, where different regions may have different properties or even different effective laws of physics. These ideas are speculative. We do not yet know whether the multiverse is real or whether our universe is finite or infinite in extent, but the questions themselves reveal how far our understanding has come. A few hundred years ago, the Milky Way was thought to be the entire universe. A century ago, we did not know the universe was expanding. Now we can describe its history from tiny fractions of a second after its beginning to the formation of the first stars, galaxies, and planetary systems. We can map the cosmic web, weigh dark matter, and detect the faint afterglow of the Big Bang itself. The future of the universe is another open chapter. If dark energy remains constant, expansion will continue to accelerate. Over unimaginably long timescales, stars will burn out, galaxies will fade, and the cosmos will grow colder and darker. Proton decay, if it occurs, would eventually dissolve even the matter in atomic nuclei. Black holes would slowly evaporate through Hawking radiation. We live in a bright, active epoch when stars are still shining and galaxies are still forming. This is a temporary phase in a much longer story. There are other possibilities. If dark energy changes in strength or in nature, the expansion might slow, stop, or even reverse. Some speculative scenarios imagine a big rip in which accelerated expansion eventually tears apart galaxies, stars, planets, and even atoms. Others explore cyclic universes where expansion is followed by contraction and a new beginning. At present, observations favor a universe that will keep expanding forever, but our knowledge is incomplete and surprises are always possible. What we can say with confidence is that the universe has a history and that we are part of it. The grand beginning was not a single explosion that threw rocks into empty space, but the start of an ongoing process, the expansion and cooling of space, the emergence of structure, the birth and death of stars, and the rise of complexity from simplicity. To ask where the universe came from is to ask about this entire chain of events, from quantum fluctuations in a primordial field to the formation of galaxies and the appearance of observers who can contemplate all of it. When we look up at the night sky, we are not just seeing points of light. We are looking into time, across vast distances, into earlier chapters of the same story. A faint galaxy in a deep field image is not just a speck. It is a young system, seen when the universe was a fraction of its current age, busy forming stars in an environment very different from our own. The cosmic microwave background is not just noise on a radio receiver. It is light emitted when the universe was a hot fog of hydrogen and helium long before the first star was born. The universe's grand beginning set everything in motion. From that hot, dense state have come clusters, filaments, voids, galaxies, stars, planets, oceans, forests, cities, telescopes, and minds that can tell this story. We do not know whether the universe had a deeper cause or whether it is part of a larger structure we cannot yet perceive. But within the observable cosmos, we see clear evidence of an unfolding, evolving reality. To understand the universe from its beginning is to understand that nothing about our existence is ordinary. Every law of physics that held in the first second still holds now. Every pattern we study in galaxies echoes patterns first etched into the fabric of space billions of years ago. We belong to this history. Our thoughts, our questions, our curiosity are ways the universe is becoming aware of itself.